Hi, this is take 3. No matter what, I'm keeping this one. All right, chapter 10, gases. We're skipping to chapter 10 for this one. The gas law unit should be fairly easy for us conceptually to understand because we're surrounded by gases all day. We've all messed with balloons. We've all seen a flat tire. So we kind of get the common sense properties of gases already. All right, so some things to be careful of though. Whenever you're doing math with gases, the temperature has to be in Kelvin. That's going to be fine now. It's just going to get confusing later because whenever you're doing the math for heat, whenever you're doing thermochemical calculations, the temperature has to be in Celsius. So just try not to get those mixed up. Right now, just keep the temperature in Kelvin. All right, as always, oh, no, you don't. Hold on. Postpone. All right, as always, you need to make sure to label your units, especially in conversion factor work. And then the last one we'll worry about later. Okay, so big surprise, all substances have 3 phases: solids, liquid, or gas. Now, if a substance is normally a gas at room temperature, like oxygen or helium, we call it a gas. But if it's normally a solid or a liquid at room temperature, then we call it a vapor. That's why we don't say water gas, we call it water vapor, because water is normally a liquid at room temperature. So, trying to think of another example, but water is unique in that we frequently in everyday lives get to see it in all 3 states. We get to see it as a vapor when we exhale on a cold day or watching a pot of water boil, and we see it as a liquid every time we wash our hands, and we see it as a solid in ice cubes. So if you think about it, there's nothing else that you see in all 3 states that frequently. All right, so if it's normally not a gas, you call it a vapor when it is a gas. But if it's normally a gas, you call it a gas. Now, probably one of the most significant properties of gases is that the molecules are very, very, very far apart. There's a whole lot of empty space. You just don't have that with solids and liquids. The molecules are closer together. So because of that, the gases are unusual compared to liquids and solids. They're highly compressible because of all that space in between them. If you apply pressure, you can squeeze them a lot closer together. The gases spread out and fill up the full volume of their container. So because all that space in between them, when you subject that gas to pressure and squeeze it, it'll shrink into a smaller volume. It's harder to do that with solids and liquids, of course. Now, when you mix 2 gases together, they immediately form a homogeneous mixture with the other gases already present. No need to stir, basically. That's why if somebody sprays some perfume in one corner of the room very quickly, we will all know about it because the gaseous molecules just move around so fast. All right, because they are so spread out though, if you could actually see the gas molecules, they make up a very small part of the volume of their container. So in the whole classroom, all those gas molecules that are flying all over the classroom wouldn't even make up a balloon's worth, I guess, of gas molecules. They are so spread out. There's so much empty space between them. So the thing about that is it actually makes our lives easier when it comes to doing mathematical calculations. Because the gas molecules are so far apart, they behave like they're alone in the container. So we don't usually need to consider how the molecules are attracted to one another or how they might be repelled by one another. Because there's so much space in between them, they're not interacting at all. We don't have to worry about intermolecular forces like London dispersion forces, usually under normal gas conditions. All right, some common gases that you'll see. These are all gases at room temperature normally, so these we will see in our calculations a lot, so just get ready to hear those. Remember, ammonia is just NH3 gas. Ammonium, NH4 plus, is the ion that's formed when it dissolves in water. Don't get those two confused. All right, what is the major reason that physical properties do not differ much from one gaseous substance to another? Meaning, why is the density of oxygen not that much different than the density of nitrogen? Or why is their boiling point not that much different? Well, gases generally have very low molecular mass. It's true, there are some heavier ones, but And then the next one, gases have high kinetic energies. Kinetic energy is just the energy of motion, and they do move very fast. Number 3, in gases, the distance between molecules is relatively large. That is true. In gases, the attractions between molecules are large. That's false. Remember, we said they're so far apart that the molecules don't really seem to notice each other and don't repel or attract each other much. So the first 3 are true, but the major reason, it always comes down to that distance between the molecules. They are so far apart. Their gases are mainly empty space, so all gases then tend to be kind of similar to one another for that reason. All right, pressure. Pressure is one of the characteristics we're going to measure about gases. Pressure is just the force acting on an object per unit area. So the most common unit of pressure that you've probably heard of in everyday life is PSI, what we measure our tires in, pounds per square inch. That just means the molecules are colliding with the walls of the tire with so much force that there's that many pounds of pressure per every square inch of tire surface. So that's what causes pressure, is the collisions of the gas with the walls of whatever container it's in. All right, there's a whole lot of units for measuring pressure. The official SI one is Pascal. That's used a lot in physics. We'll have it pop up every now and then. A related unit is the bar, which is equal to 10 to the 5th pascals. That little K should not be there. That's a typo. So we have pressure all the time on the surface of the planet. That's because gravity exerts a force on the Earth's atmosphere. So atmospheric pressure at sea level is about 1 bar. The actual, or 1 atm, is another unit you might have seen already. The actual atmospheric pressure at specific location does depend on the altitude and the weather conditions. So I want you to think about though why there's less pressure up when you're up in the mountains. Why is that? Why would there be less atmospheric pressure when you're at high elevations? See if you can think of that for class. All right, so when we talk about atmospheric pressure, we're simply talking about the force of gravity pulling on a square meter of air all the way up through the atmosphere. So that would be equal to about 10 to the 4th kilograms of air. So in a square meter, gravity is pulling down 10 to the 4th kilograms of air on top of us. And we don't notice it because it's just always been there, but that's quite a bit of pressure if you think about it. All right, so how do we measure atmospheric pressure? Well, a guy named Torricelli, way back when, had a really big giant house with like a big multi-story entryway, and he built a giant barometer type thing to measure pressure with. So what he did was took a tube, filled it completely to the top with mercury. We're not going to be doing that for obvious reasons. And then inverted it into a container of mercury that was open to the atmosphere. And the atmosphere pushed on that mercury with enough force to make the mercury rise up the tube 760 millimeters. So it's kind of weird. Oh, I get the itchies. Sorry, it's kind of weird that we would measure pressure in millimeters and then of mercury at that. But once you see this picture, it kind of makes sense. So there's about 1 atm of pressure pushing on this mercury, which then pushes it up this tube to a height of around 760 millimeters. So that's how a barometer works. Now, a standard atmospheric pressure that's the definition of it, the amount of pressure needed to support that column of mercury. Other non-SI units that we'll see a lot for expressing gas pressure is the atmosphere, 1 atm. That's equal to 760 millimeters Hg. Now, just for some added excitement, there's another unit that means the same thing as millimeters Hg. It's called torr, named after Torricelli, the inventor of the barometer. Now, that's also equal to 1.01 times 10 to the 5th pascals. Sorry, my little image is blocking that out. Or 101 kilopascals, which is also equal to 14.7 psi, pounds per square inch. And all right, those are the ones we're going to see the most. These are all in your note packet that I gave you already, so you don't have to write them down. So we've got a millimeter of mercury is the exact same thing as a torr. 760 milligrams or torr is equal to 1 atm, which is also 101,000 pascals or 101 kilopascals. All right, you can try those if you want before class, or you can wait to work them out in class. These are just basic conversions of pressures into different units. All right, now for the fun part, the gas laws. You've done these in Chem 1. As I said, we're just going to be taking up the difficulty level a little bit. But you've seen all these variables thrown together in algebra equations before. P is for pressure. We've already talked about that. V is volume, which is just how much space a gas takes up. T is temperature in Kelvin, always. And then N is going to mean numbers of moles. So the pressure-volume relationship, the first one we're going to talk about, is known as Boyle's law. Weather balloons are probably the most commonly known application of Boyle's law. As the weather balloon ascends, as it goes up, the volume increases. Why? Because as it gets further from the surface of the Earth, atmospheric pressure decreases. Okay, we already said as you go up into the mountains, there's less atmospheric pressure. I wanted to see if you guys could think of why that is. But as the pressure goes down, the volume goes up. If you remember the PTV card I gave you, as pressure goes down, volume goes up. You can rotate that. Hopefully you can picture that in your head. So here's a graph of what it would look like. The volume of a fixed quantity of gas. We're assuming that moles are held constant here. And the temperature is also held constant. The only thing we're changing is P and V. So the pressure is going to be inversely proportional to the volume and vice versa. Okay, inversely proportional is a fancy way of saying when one goes up, the other goes down. So mathematically, that's represented as P1 V1 equals P2 V2. That's Boyle's law. All right, so here's a thinking question. What happens to the volume of a gas if you double its pressure, say from 1 atm to 2 atm, while its temperature is held constant? So you're keeping everything the same, except you're doubling the pressure. What will that do to the volume? Now remember, we're talking about the pressure that's surrounding the gas, the pressure that's pushing on the container that the gas is in. Kind of hard to explain what I'm meaning there. I need a picture. All right, so if you have a flexible container, like a balloon, and you double the pressure that's being applied to that balloon, the volume is going to decrease. Okay? If you double the pressure, the volume will be half what it was before. So when one goes up, the other goes down. All right, the lungs are a perfect illustration of Boyle's law. As we breathe in, this diaphragm, this muscle that runs beneath our lungs, moves down, and our ribs also expand. So therefore, this chest cavity, the volume of it increases. When the diaphragm moves down and the ribs move out, the volume goes up. Well, we know according to Boyle's law, when the volume increases, then that means the pressure is going to decrease. Well, suddenly then, the pressure inside our lungs is less than the pressure outside. So the atmospheric pressure then forces air into our lungs until it's equal. So it feels like we're sucking in air, but we're not really. We're allowing air to be forced in. Now, the exact opposite happens. As we breathe out, the diaphragm moves up and the ribs contract, shrinking the volume of the lungs, and that causes pressure to increase, and that forces the air out. You may want to think about that for a second. That's kind of strange. All right. Gas initially at 2 atms is in an adjustable container with a volume of 10 liters. If the pressure is decreased to a half an atm, what's the new volume going to be? Okay. This is not the picture for this problem, but this is the kind of device they're talking about. A piston, if you know car engines and stuff, you'll get this, but it's just a cylinder, and this moves up and down, kind of like just a syringe with a plunger. Not that you guys mess with syringes a lot, but 2 atm, it's cut in half and then cut in half again, the pressure is. So what's that going to do to the volume? I'm running out of time, so we're going to have to stop here on this question.